Hi guys, welcome to your 10-3 notes. Today we will be simplifying radical expressions. It's such a radical idea. By the end of the day, you will be able to simplify a radical expression. Now let's quickly review what are the parts of a radical expression. This is so that when I refer to them, you'll know what I'm talking about. So a radical is this symbol right there. This guy is called the radical. And whatever we have underneath our radical sign, we call this our radicand. Radicand, because you guys can do this, the radicand. So your radicand can be just x, or it can be x squared minus 5, or it could be 5, it could be 5, or something. Whatever you have underneath your radical, that is your radicand. And then there's one more part. There is your index. The part right here, that little number is called your index. Today your index will always be 2. If you just have this symbol that implies that your index is 2, we call it a square root. This can be any integer. You could say it's the 3rd root of something or the 5th root of something. But usually when you just have a radical, we're talking about square roots. Okay, so your radicand is what is inside your radical. That's going to be the most important part that we're talking about today. So if we have a radical expression like this one, and we want to simplify it, we need to make sure 3 things are happening. First of all, the radicand cannot have any square factors in it. You can't have any squares underneath your radical. So we say they do not have perfect square factors. To determine if it has a perfect square factor, we are going to write the prime factorization of the radical. And then once we have the prime factorization out, we can take all of the square factors outside of our radical. So the first condition is there are no perfect square factors. The second condition is that the radicand, again the thing underneath your radical symbol, your radicands cannot have fractions in them. So no fractions. And then finally, no radicals, that's the black part, this symbol, no radicals should ever be in the denominator of a fraction. Remember the denominator, that's the bottom part of a fraction. To make sure that that doesn't happen, we're going to do an expression. We're going to do something called rationalizing the denominator. To make it like a ratio, we're going to rationalize it, getting rid of its radical. So here are our 3 steps. Now for each of our 3 steps, let's draw a little symbol to help us remember them. First, no radicands can have perfect square factors. So let's say we don't want anything squared. It's going to be a bad idea. We want no squares. And then second, no radicands can have fractions. So if we draw a little fraction, we don't want any fractions. And then finally, no radicals can be in the denominator of a fraction. That means if we have, well, I guess we should say, we don't want any fractions underneath a radical. So we need to write it like that. And then finally, no radicals in the denominator of a fraction. So we can't have something that looks like that. Yeah, because these are all bad. Let's not put them under these. That's going to be hard to read. In fact, we'll make them all red because red means bad. Don't have these things. Okay. Now what I'm going to do is I'm going to copy this and I'm going to bring it down to all of our examples, and we're just going to make sure that none of these conditions are met. Ready? Let's go. So here we go. The square root of 75. With the square root of 75, let's prime factor it and see if it has any square factors. So the square root of 75 is, 75 is 3 times 5 times 5. Now you'll see that I have two factors here. 5 times 5, that's the same thing as 3 times 5 squared, and that's going to be a perfect square. So we can use the product property of radicals to split this up. So the square root of 3 times 5 squared is the same thing as the square root of 3 times the square root of 5 squared. The square root of 5 squared is 25. And the square root of 25 is 5. I'll bring this down here. Now this can be a little confusing that I put this 5 afterwards. It looks kind of messy, like is that still underneath the radical? And it's not. So what I'm going to do instead is I'm going to reorder them. I'm going to put the 5 first, and I'm going to put the radical second. 5 times the square root of 3. So going backwards, I got 5 times the square root of 3 because 5 is the square root of 25 and the square root of 3. I got 25 because that's 5 squared. We said 5 squared because we have two 5s. Now that meets our no perfect squares rule. Do we have fractions? No. Is this a fraction? No. So that is the square root of 75 in its most simple form. 5 times the square root of 3. Let's do another one just like that. The square root of 68. Let's write out the prime factorization and see if we have any perfect squares. First, I know that's divisible by 2, 2 again, and 17. Cool. Hey look, we have two 2's. So we can write that as the square root of 2 squared times 17. Now we're going to split it up. It's the same thing as the square root of 2 squared times the square root of 17. And the square root of 2 squared is the square root of 4. Or you can say, hey look, these square roots with the squares, that cancels out. Sweetums. So that gives us 2 times the square root of 17. That's it. We simplified it. On to our next one. The square root of 3 times the square root of 15. We have a couple options here. We could say, oh, the square root of 3 times the square root of 15, that's equal to the square root of 3 times 15, which is the square root of 45. And we can follow the same process that we did up here. We can split 45 up and prime factor it and then keep going. Or we can skip that step and split it into the individual radicals, which we're going to do now. So we're going to keep the square root of 3 the same. Cool. And now we're going to mess with the square root of 15. Well, that's the same thing as the square root of 3 times 5. And now we can split that radical up. So keeping our square root of 3 the same. That's the square root of 3. And then we can split this guy into the square root of 3 times the square root of 5. Yay! Next, the square root of 3 times the square root of 3. Well, that is 3. Add 5. All done. Next. Let's do a very, very similar one. So here again, we could multiply 5 times 35 together and get 100 something, or we can just split it up right away. So okay, that's the same thing as the square root of 5 times the square root of 5 times 7, which is the square root of 5 times the square root of 5 times the square root of 7, and then the square root of 5 times the square root of 5 is just 5. times the square root of 7. If you're confused on how I got the square root of 5 times the square root of 5 is 5, well, let's do it this way. Square root of 5 times square root of 5, that's the same thing as square root of 5 times 5, and the square root of 5 times 5 is square root of 25. Guys, what's the square root of 25? It's 5. Yay! Equals 5. Super duper. So that's where we got the square root of 5 times 5 is 5. Yay! Moving on. Oh no, guys. We have some fractions. Fractions are not okay. So what I like to do is I like to simplify the numerator first, and then we'll simplify the denominator and see what we can do from there. Okay, square root of 32. Well, we could prime factor it and say that's 1, 2, 3, 4, 5. That's a lot, but it's doable. We can split these in two. 2 times 2 is 1 square. 2 times 2 is another square. So that's equal to the square root of 4 times 2. And then, hey, look, we have another square root. 4 times 4, that's 16. So that's the square root of 16 times 2. Or if you knew and you looked at 32 and you said, hey, what's the biggest square that's in 32? And the biggest square is 16. Sweet. So I'm going to leave that there, and I'm going to go back for the denominator. Let's simplify the denominator. Okay, the square root of 4. That's the same thing as the square root of 2 times 2. Or, hey, the square root of 4 is 2. Yay. But just to show you one more step, that's the same thing as the square root of 2 times the square root of 2, and those are 2, because, you know, 1 square root times the square root is 2. Super. Okay, so here, let's bring this guy down. So we have the square root of 16 times 2 all over 2. We're almost there. We can break this up as the square root of 16 times the square root of 2 all over 2. Guys, what is the square root of 16? 4. Good job. And then finally, we have our 4 and our 2 cancel out. So we can make this a 2 and this a 1. So our final answer is 2 times the square root of 2. Check our work. We have no squares under our radical. We have no fractions. Therefore, we don't have any radicals in our denominator. Okay, let's look at number 6. So number 6, we're going to do the same thing. I'm going to look at the numerator, and then I'm going to look at the denominator. So 72. Well, I could say to myself, hey, 72, that's 36 times 2, and 36 is 6 squared. But if you didn't know that, we can break that up. So let's prime factor 72. Let's take the opportunity to review the prime factorization process. So we start out with 72, and I look at 72 and I think, well, 72, that's 8 times 9. Now, is 8 prime? No, it is not prime, so we need to keep going. 8 is 4 times 2. Oh, and 2 is prime, so we can stop there. But 4 is not prime. We can split 4 into 2 times 2. Done and done. Now 9 is not prime. We can split 9 into 3 times 3. Now that we have all of our factors are prime, we say that 72 is 1, 2, 3 2s and 2 3s. So we could say, hey, 72 is equal to 1, 2, 3 2s and 1, 2, 3s. Or, if you're like me, you like to write that 72 equals 2 to the third power times 3 to the second power. And we're going to use this fact to help us simplify our radical. So because 72 equals 2 cubed times 3 squared, you know what, guys? We should have written it the other way. We're going to say that that's 1, 2, 3, 1, 2. 72 is 2 3s, and is 3 2s and 2 3s. Okay. Now we can split this up into some perfect squares. Here we have a 2 times 2 and a 3 times 3. So that's the same thing as the square root of 4 times 2 times 9. And we're going to leave that there because I ran out of room. I guess I could shrink this. Maybe Notability says, you know what, Miss Van Dyke? Don't shrink it. There we go. Nice. Okay, so while we're there, we can break this up into the square root of 4 times the square root of 2 times the square root of 9. Okay, let's work on our denominator. 6 is the same thing as 2 times 3, so we can also split that up into square root of 2 times the square root of 3. Okay, now let's rewrite what we have. So we have the square root of 4 times the square root of 2 times the square root of 9 all over the square root of 2 times the square root of 3. We're almost there. When I look at this, I see that the square root of 2's, those are going to cancel out. Super. And the square root of 4 is 2. The square root of 9 is 3 all over the square root of 3. 2 times 3 is 6 divided by the square root of 3. Okay, how did we do? Well, we no longer have a square under our radical. We don't have the square root of a fraction. We don't have a fraction in our radical. Oh no, guys. We have a radical in our denominator. This is no good. This is not allowed. So how can we clean this up? You guys, this is what is called rationalizing the denominator. We're going to make it rational because the square root of 3 is not a rational number. So we're going to turn our denominator into something rational. And how we're going to do that is we are going to multiply by what we want to get rid of. We have that square root of 3. We want to multiply by the square root of 3 over itself. This is because anything divided by anything is 1. We can multiply by 1, and that's fine. So we're not really doing anything to it. We're not changing the value. We're just doing a really fancy way of multiply by 1. Multiply by 1, but super trickily, sneakily. I like that. Sneakily. Because again, multiplying by 1 doesn't change anything. So we're being super sneaky about it, but it's going to look really pretty. Okay, so here we go. So on top, 6 times the square root of 3. Guys, it's 6 times the square root of 3. Awesome! And then the square root of 3 times the square root of 3 is the same thing as the square root of 3 times 3. Oh, that's just 3, because the square root of 9 is 3. And guys, that will always be the case. You will always get it where here, if you're trying to rationalize the denominator, so you do the square root of something times the square root of that same something, you will always get this back. That is, if you have you know, the square root of a number times the square root of a number, that's always equal to that same number. Just like the square root of 25 times the square root of 25, which is 5 times 5 equals 25. Yay! So we're going to use that fact here. And then we're almost done. The 6 and the 3 cancel out to get 2 and 1, giving us 2 times the square root of 3. That's much more simpler than the square root of 72 divided by the square root of 6. We're going to do 2 more like that, and then we'll be on our way. So here we have the square root of 5 divided by the square root of 10. Now it's nice. We don't have any perfect squares. We don't have a fraction underneath our radical, but we do have a radical in the denominator. That is yuck, and we don't want to do that. So instead, we're going to do that trick that I just taught you. We're going to rationalize the denominator. So we want to get rid of the square root of 10. So we're going to multiply top and bottom by the square root of 10. Cool. So on the top, that will give us the square root of 5 times 10, which is the square root of 50, all over. Square root of 10 times the square root of 10 is 10. Yay! This is because we get the square root of 10 times 10, which is the square root of 100, which is 10. Super duper. Okay, so here, I look at this 50 divided by 10, and I can't just say, oh, that's 5, because 50 divided by 10 is 5. That is not going to be the case, because we've got this radical here. And that's not even the same thing as the square root of 5. To keep that radical here, we can't do that either. We started with the square root of 5. The square root of 10, we can't just pretend that didn't happen. So this is not the right way to go. But what we're going to do is we're going to simplify the square root of 50. 50 is the same thing as 2 times 25. I like this 25 because 25 is a perfect square. So I can split that up, and that gives me the square root of 2 times the square root of 5 all over 10. I'm sorry, I got ahead of myself. Square root of 25 is 5 all over 10. Now we're almost there. 5 and 10 cancel out, give me 1/2. So we have the square root of 2 all over 2. That was supposed to be a box. Good enough? Awesome. But wait, Miss Van Dyke, we have a fraction. Isn't that against our 3 rules? Great question, guys. It's not against our rules. We just can't have a denominator that's touching a radical symbol. And here our denominator is fine. We have a radical in the numerator, and that's okay. But we do not want one in the denominator. Since that's what we have, we're okay. And finally, square root of 6 divided by the square root of 8. Let's simplify top and bottom and find out what we get. So here we have the square root of 6 is 3 times 2, and 8 is the square root of 4 times 2. Interesting. I'm going to like this one a lot, guys. You know why? We can split this up. Square root of 3, square root of 2, and what is the square root of, oh, I'm sorry, I got ahead of myself. I was so excited. Square root of 4 times the square root of 2. Oh, guys, check it out. Our square root of 2 and the square root of 2, those are going to cancel out. So we have the square root of 3 divided by the square root of 4. But what's the square root of 4? It's 2, giving us the square root of, the square root of 3 all over 2. Haha, done. Love it. So fun fact, these last two that we did, rad 2 over 2, the square root of 2 divided by 2, and rad 3 over 2, rad 3 over 2, those are very important in advanced math. Oh, we love them. They're very important for what we call trigonometry, which is the study of triangles. And if you go on to geometry, you're going to learn all about SOHCAHTOA, which is, oh, guys, I'm getting so ahead of myself. Those are very important numbers. Just know they lie on the unit circle, and they're great, and we love them. So, they're awesome. Alright, that's awesome, but when are we going to use this in real life? I'm so glad you asked. Well, on a softball field, the distance from second base to home plate, so pardon my amazing drawing, second base to home plate is the square root of 800 meters. So we're going to express the square root of 800 in simplest radical form. We could prime factor it, but I'm going to save you some time. We would end up finding that the square root of 800 is the same thing as the square root of 400 times the square root of 2. Now 400 is nice because that is a perfect square. 400 is 20 squared. So this gives us 20 times the square root of 2. And we're all set. Next, we have the radius of a circle is the square root of 32 meters. So if this distance is the square root of 32, we want to express that in simplest form. So the square root of 32. We could prime factor it. I'm going to save you some time. We'd find out that that is equal to the square root of 16 times the square root of 2. And 16, you'll remember, is 4 squared. So that is equal to 4 times the square root of 2. And we're all set. So again, when you are simplifying radicals, you need to keep 3 things in mind. First, make sure that the radicand does not have a perfect square factor. Secondly, make sure that in your radicand you do not have fraction. And finally, make sure that if you have a fraction, you do not have a radical in your denominator. You need to remember to rationalize the denominator. On your homework, make sure each of these is true, and you will have your correct answer. Enjoy the process.